Most of the universe is made of something we cannot see. This invisible substance, known as dark matter, holds galaxies together and dictates the cosmic order, yet it remains a ghost. We are not just exploring what dark matter is, but the hidden engine that powers its silent influence over everything. By the end, you will understand the fundamental forces that orchestrate the cosmos, from the spin of galaxies to the fate of the universe itself. How could something we cannot touch shape the reality we live in? And what does its secret nature reveal about our own place in the grand scheme? What part of this cosmic mystery most captures your own imagination? A vast, dark ocean flows through the cosmos, its invisible currents shaping everything they touch. We are adrift in this sea, feeling its pull without ever glimpsing the substance itself. This is our relationship with dark matter. We know it is there because of its relentless gravitational handshake. Galaxies spin so fast that the stars on their outer edges should be flung into the void, yet something holds them in place. Light from distant galaxies warps and bends as it travels past immense cosmic structures, revealing the presence of an unseen mass bending the fabric of space itself. The story of this discovery begins nearly a century ago with an astronomer named Fritz Zwicky. Studying the Coma Cluster, a sprawling group of galaxies, he realized the individual galaxies were moving far too quickly. The visible mass of all those stars was not nearly enough gravity to hold the cluster together. He proposed the existence of Dunkel Materie, dark matter, to account for the missing glue. Decades later, Vera Rubin provided the definitive evidence, meticulously mapping the rotation of galaxies. She found those outer stars orbiting at the same speed as the inner ones, a clear violation of the laws of gravity, unless a massive halo of unseen matter enveloped each galaxy. So what are the properties of this cosmic ghost? Dark matter does not emit, absorb, or reflect light. It passes through the ordinary matter you and I are made of as if it were not even there. Its only known interaction is through gravity, the weakest of the fundamental forces, yet its influence is absolute on the grandest scales. This brings us to the staggering scale of the problem. The atoms that make up every star, planet, and person account for less than 5% of the universe. Dark matter, this invisible scaffold, makes up 27% of everything. It is the dominant architectural material of the cosmos, the hidden framework upon which the visible universe is built. With such pervasive influence, the question becomes unavoidable. What kind of engine could possibly power something so fundamental, yet so completely elusive? Gravity is the silent language of the cosmos, a conversation written into the fabric of space and time. It is not merely a force pulling apples from trees, but the universe's master conductor, orchestrating the motions of everything from the smallest moon to the largest supercluster. And in this grand symphony, dark matter is the primary instrument, its gravitational voice the only one loud enough to command the cosmic stage. We hear this orchestra, but we have never seen the musicians. To understand this, we must look to Einstein's revolutionary insight. His theory of general relativity reimagined gravity not as a simple pull, but as a curvature, a warping of the very space-time continuum caused by mass and energy. Think of space-time as a vast, taut rubber sheet. Place a heavy bowling ball in the center, and it creates a deep well. Now, roll a marble nearby, and its path will curve, orbiting the larger mass. This is gravity. Dark matter is an immense, invisible weight scattered across that sheet, creating a landscape of profound dips and valleys that guide everything else. As cosmologist Priyamvada Natarajan has eloquently explained, these dark matter halos are the fundamental skeletons of the universe. They form first, vast and diffuse clouds of this mysterious substance collapsing under their own gravity. These halos become deep gravitational wells, cosmic traps that capture the ordinary atomic matter we are made of. Without this hidden framework, the gas and dust necessary for star formation would simply drift apart, never coalescing into the brilliant galaxies we see today. The Milky Way itself is embedded within a colossal halo of dark matter, a sphere of invisible influence that extends far beyond its visible stars. This gravitational engine did more than just build the universe. It set the tempo for its entire evolution. Every galaxy we observe is a testament to the shaping power of this unseen hand. So if gravity is the only way dark matter speaks to us, what exactly is it that is doing the talking? What unseen particle could possibly embody this cosmic force that frantic search for the cosmic key continues deep underground, in abandoned gold mines, and within the world's most powerful particle colliders? For decades, scientists have been chasing a ghost, trying to identify the fundamental particle that constitutes dark matter. The leading candidate has a name that sounds almost too perfect: the WIMP. This stands for Weakly Interacting Massive Particle, and it represents a hypothetical class of particle that could perfectly explain everything we observe. The appeal of the WIMP is rooted in what physicists call the WIMP Miracle. It is a stunning piece of cosmic serendipity. Calculations show that if a stable particle with a specific mass, roughly tens to hundreds of times heavier than a proton, interacted only through gravity and the weak nuclear force, it would have been forged in the incredible heat of the Big Bang in just the right quantity. The predicted relic abundance of these particles, left over from the universe's first second, matches almost exactly the amount of dark matter we measure today. It is a solution so elegant it feels almost too good to be true. So what would a WIMP actually be like? It must be massive enough for its gravity to pull matter together, forming those cosmic scaffolds for galaxies. Yet it must be neutral and incredibly shy, interacting with ordinary matter so rarely and weakly that it simply passes through our planet, and through us as if we were made of air. This dual nature is the entire point. It is massive enough to shape the universe, but weakly interacting enough to remain completely invisible. The hunt for this phantom particle takes two main forms. At facilities like the Large Hadron Collider, physicists are trying to create WIMP by smashing protons together at nearly the speed of light, hoping to see a missing energy signature that would signal the birth of an invisible particle. Meanwhile, in deep underground labs shielded from cosmic rays, experiments like LUX Zeppelin wait in profound silence. They are essentially ultra-sensitive buckets of liquid xenon, waiting for the once-in a lifetime event where a passing WIMP might nudge an atomic nucleus, creating a tiny flash of light and a whisper of charge. Catching that single, rare interaction would confirm a hidden engine that has been running since the dawn of time. But what if the WIMP miracle is just a beautiful dream? The fact that we have not found them yet forces us to ask if the engine of dark matter is something even stranger, something we have not yet dared to imagine. That cosmic blank canvas was not perfectly smooth. In the searing heat of the first moments after the Big Bang, it was imprinted with the faintest of imperfections, tiny quantum ripples in the fabric of space-time. These ripples were the universe's original seeds, and gravity was the force that would make them grow. But there was a problem. Ordinary matter, the protons and electrons that would one day become us, was locked in a desperate struggle with light. Photons of intense radiation pushed against the atomic gas, creating a pressure that prevented it from collapsing into the dense structures needed to form galaxies. The universe needed a different kind of material, one that was immune to this cosmic pressure, a substance that could feel gravity's pull but was blind to light's push. That substance was dark matter. Because dark matter does not interact with light, it was free to respond to gravity's quiet call from the very beginning. Those tiny quantum ripples became the blueprints. Slightly denser patches of dark matter began to pull in more dark matter from their surroundings, growing steadily over hundreds of millions of years. They clumped first, forming a vast, invisible network of gravitational wells long before the first star ever flickered into existence. This is the cosmic web, a sprawling architecture of dark matter filaments connecting at dense nodes, a hidden skeleton upon which the visible universe would eventually be draped. We can see this grand design not with telescopes, but with supercomputer simulations like the famous Millennium Run. These digital universes show the clear prediction, starting with the observed primordial ripples and letting the laws of physics play out. The result is a stunning cosmic map of dark matter tendrils, a web of invisible threads where galaxies are destined to form. As cosmologist Carlos Frenk has described it, dark matter provides the invisible backbone of the cosmos. Once these dark matter halos were in place, their immense gravitational pull became irresistible. They acted as traps for the ordinary atomic gas, which could now flow into these pre-existing wells, cooling and condensing until it ignited into the first brilliant stars. This sequence is crucial. Dark matter laid the foundation, and ordinary matter simply followed its blueprint. This is why we see galaxies clustered along these invisible lines, strung across the cosmos like pearls on a string. The great walls and vast voids of our universe are not random. They are the direct imprint of that initial dark matter template. The evidence for this invisible architecture is written across the night sky, in the very distribution of every galaxy we can see. Light itself bends to the will of the unseen. A distant galaxy's light, traveling for billions of years to reach us, does not always follow a straight line. Its path is curved by the immense gravitational fields of dark matter it passes, acting like a cosmic funhouse mirror that warps our view of the distant universe. This phenomenon, gravitational lensing, is one of the most direct proofs of dark matter's pervasive presence and a powerful telescope for the invisible. It works because, as Einstein revealed, mass curves the fabric of spacetime. Light, always following the straightest possible path through this curved geometry, appears to bend from our perspective. A massive object, like a cluster of galaxies embedded in its vast dark matter halo, acts as a natural lens. When a distant galaxy is directly behind this cosmic lens from our viewpoint, its light is stretched and smeared into brilliant arcs, or even multiplied into several images surrounding the cluster. This is strong gravitational lensing, a dramatic and unmistakable signature of hidden mass. But the subtler effects are just as revealing. Weak lensing occurs when the dark matter distribution is more diffuse, not creating perfect arcs but imparting a slight, coherent distortion to the shapes of thousands of background galaxies. Individually, each distortion is tiny, but by analyzing the statistics of how countless galaxies appear subtly stretched and aligned, astronomers can draw a map of the intervening dark matter. Projects like the Hubble Space Telescope's frontier fields have used this technique to peer deeper than ever before. They aim Hubble at massive galaxy clusters, using these natural telescopes to magnify the faintest, most distant galaxies behind them. In the process, they map the cluster's dark matter halos in exquisite detail, revealing how this invisible scaffold dictates the arrangement of both the luminous galaxies and the magnified background light. This is how we see the unseeable. We are not looking for the dark matter itself, but reading its shadow in the distorted light of the cosmos. It is a ghost writing its name in the stars, a compelling piece of evidence that forces us to ask what other profound distortions this hidden engine is creating across the universe. Our search for the cosmic ghost leads us into the realm of theoretical mirrors. Picture a hidden, more complete version of our universe, where every particle we know, every electron and quark, is paired with a heavier, more exotic superpartner. This is the elegant promise of supersymmetry, a theory that could supply the universe with a whole zoo of potential dark matter particles. The lightest of these superpartners would be stable and neutral, a perfect WIMP candidate falling gracefully out of the mathematics. Supersymmetry offers a profound answer. suggesting our hidden engine is not a single entity, but a diverse family of particles waiting to be discovered. Yet this beautiful symmetry remains unproven, a ghost in the machine of particle physics itself. Another compelling candidate emerges from a different cosmic puzzle entirely. Deep within the rules governing the strong nuclear force, the glue that holds atomic nuclei together, physicists found a troubling asymmetry that should make the universe look very different than it does. To solve this, a hypothetical particle was proposed: the action. These particles would be born in the early universe, not as massive WIMP, but as entities trillions of times lighter than an electron. Their incredible lightness is balanced by their staggering abundance, potentially forming a coherent, wave-like fluid that permeates all of space. Unlike the rare, nuclear bump of a WIMP, an action would reveal itself through a magical transformation. In the presence of an incredibly powerful magnetic field, an action could convert into a faint microwave photon. This is the principle behind ambitious experiments like ADMX, led by scientists such as Dr. Leslie Rosenberg. Their apparatus is essentially a high-tech radio receiver, tuned to the precise frequency at which a dark matter action might whisper into existence as a detectable photon. It is a hunt for a note in a cosmic symphony, a signal so quiet it is easily lost in the noise of the universe. The existence of such different candidates, from heavy WIMP to ultra-light actions, reveals a profound truth. The engine of dark matter might be more complex and wondrous than we ever imagined. Our search must now widen, exploring not just one possibility but many, forcing us to question if the answer lies in a particle we have already conceived, or one that awaits a moment of pure, revolutionary insight. That whisper in the hurricane is what physicists are straining to hear. For decades, ambitious experiments have been constructed to catch the faintest tremor, the slightest bump, that would signal a direct encounter with a dark matter particle. These are not telescopes pointed at the sky, but incredibly sensitive traps buried deep beneath the earth. In places like an abandoned gold mine in South Dakota or under a mountain in Italy, laboratories have been carved out of solid rock. This natural shielding is essential, blocking out the constant cosmic ray shower that would otherwise drown out the elusive signal they seek. Inside these silent caverns, the heart of the experiment waits in profound darkness and cold. The most sensitive detectors use vats of ultra-pure liquid xenon, chilled to temperatures colder than the void of space. Scientists watch this liquid with exquisitely sensitive light sensors, hoping to see the tiny, telltale flash of light and the corresponding wisp of electric charge that would be produced if a dark matter particle, after passing effortlessly through miles of rock, finally collided with the nucleus of a xenon atom. It would be a 1 in a trillion event, a ghostly handshake after a journey across the cosmos. The process of eliminating background noise is a painstaking battle against the universe itself. Every material used must be meticulously selected for its ultra-low radioactivity. Even the faint natural radiation from the surrounding rock, or from the very dust in the air, must be accounted for and shielded against. Experimentalists describe this as a constant pursuit of purity, building a quieter and quieter room in which to listen for that single, cosmic whisper. Yet, despite this monumental effort, the result after decades of searching has been a profound and telling silence. Experiments like Xenon 1T and its successors have pushed sensitivity to incredible extremes, ruling out vast swaths of possible particle masses and interaction strengths. Each new, more sensitive detector is built with the hope of finally seeing a signal, only to return more precise null results. This silence is not a failure, but a powerful message from the universe. It tells us that the hidden engine of dark matter is even more elusive than our favorite theories predicted. The elegant WIMP Miracle, for all its mathematical beauty, is being cornered by this lack of evidence. This persistent quiet forces a fundamental shift in our thinking. We must now confront the possibility that the engine powering dark matter's influence is not a particle that bumps into nuclei at all, but something far stranger, something that challenges the very particle paradigm we have relied upon for so long. Perhaps the ghost is not a substance at all, but a flaw in our most trusted map. The persistent silence from deep underground experiments forces a radical question. What if we are searching for an actor that does not exist because the script itself is wrong? What if the hidden engine is not an invisible form of matter, but a hidden law of gravity? This is the bold proposition of modified Newtonian dynamics, or MOND. It suggests that on the vast, diffuse scales of galaxies, gravity does not fade away as quickly as the equations of Newton or Einstein demand. Instead, it holds on with a subtle, persistent strength. The physicist Mordechai Milgram first proposed this idea in the early 1980s, driven by the very same galaxy rotation curves that Vera Rubin made famous. He found that by introducing a new, very gentle acceleration scale into the law of gravity, the need for dark matter simply vanished. The outer stars of galaxies orbit at the observed high speeds not because of an unseen halo, but because gravity itself is stronger in those extremely low acceleration environments. It is a breathtakingly elegant solution. With a single tweak to a fundamental formula, MOND can predict the rotation of thousands of galaxies with stunning accuracy, all without a single particle of dark matter. It proposes that the engine powering the cosmos is a rewrite of the rules we thought were absolute. Yet for all its success on the scale of individual galaxies, this rewritten law faces its own monumental challenges. The most famous comes from a violent cosmic collision known as the Bullet Cluster. Here, two clusters of galaxies have slammed into one another. The visible matter, in the form of hot gas, was slowed and tangled in the middle of the wreck. But maps of the cluster's total mass, made by observing how they gravitationally lens background light, show the bulk of the mass has sailed right through the collision, residing in two regions now separated from the visible gas. For most scientists, this is the smoking gun for dark matter. It appears to show that the dominant mass is truly invisible and non-interacting, just as the WIMP model predicts. For MOND, explaining how a modified gravity law could create gravitational effects that are physically separated from the visible matter is an immense hurdle. This is the heart of the controversy. Do we invent a new, unseen substance that makes up most of the universe? Or do we rewrite the theory of gravity that has guided our understanding for centuries? The choice forces us to look beyond galaxies, to the very largest structures in existence, where the true nature of the cosmos's hidden engine may finally be written. A brilliant city of stars does not exist in isolation. Each galaxy is embedded within a vast, invisible metropolis of dark matter, a spherical halo whose gravity dictates every aspect of the city's life. These halos are the true architects of galactic destiny. Supercomputer simulations reveal their ghostly anatomy, a structure that grows denser towards the center, creating a deep gravitational well that cradles the luminous galaxy within. This hidden grip is what keeps a galaxy from spinning itself apart. The speed of stars on the outer edges, whirling at the same velocity as those near the core, is a direct measure of the halo's immense, unseen mass holding them in place. Even the swarms of ancient stars known as globular clusters are not randomly scattered. They trace the invisible contours of this dark matter sphere, orbiting its gravitational field like moths around a dim, unseen flame. Yet this elegant picture holds a puzzling flaw, one that astrophysicists like Dr. James Bullock have intensely studied. It is called the core cusp problem. The simulations predict that dark matter halos should have a sharply peaked density at their very centers, a cusp. But observations of many galaxies suggest the inner regions are more like a constant density core. It is as if the ghostly metropolis has a strangely hollowed-out downtown. This discrepancy is a profound clue. It hints that our understanding of dark matter's inner workings is incomplete, that perhaps complex interactions between dark matter and the violent astrophysics of exploding stars are smoothing out these central cusps over billions of years. This means the hidden engine is not a simple, uniform substance. It possesses a complex internal structure that evolves over time, directly sculpting the visible universe in ways we are only beginning to decipher. If a single halo can hold such intricate mysteries, what happens when these invisible giants collide and interact across the cosmic web? That fossilized light is all around us, a faint whisper from the dawn of time. This is the cosmic microwave background, the oldest light in the universe. It is a snapshot taken when the cosmos was a mere 380,000 years old, a glowing fog of plasma that finally cooled enough for atoms to form and light to travel freely. Today, we observe this light as a uniform microwave glow, the cooled and stretched remnant of that primeval fire. But when we look closely with instruments like the Planck satellite, we find it is not perfectly smooth. It is imprinted with a tapestry of minute temperature variations, hotter and colder spots that represent the earliest seeds of all cosmic structure. These tiny ripples are the universe's original blueprint, and their specific pattern holds an undeniable signature. The way these hot and cold spots are distributed, their precise sizes and statistical relationships, can only be explained if a significant portion of the universe's matter was a type that could clump together under gravity long before ordinary matter could. Atomic matter was still buffeted by radiation pressure, sloshing in waves that prevented it from collapsing. But dark matter, indifferent to light, was free to fall into those initial gravitational wells. Scientists from the Planck collaboration have stated that the data is unequivocal. The patterns etched into this cosmic baby picture demand that roughly 27% of the universe must be composed of this cold, collisionless dark matter. Without it, the acoustic peaks in the CMB power spectrum, the specific statistical fingerprint of those temperature fluctuations, would look completely different. This is our most powerful evidence that the hidden engine was not a late addition. It was there from the very first moments, actively sculpting the distribution of matter and setting the stage for everything that was to come. Its gravitational influence is literally frozen into that first light, a permanent record of its foundational role. This fossil not only confirms dark matter's existence, but also tells us its precise contribution to the cosmic budget, forcing us to confront a profound question. If this invisible substance dictated the universe's birth, what role does it hold in determining its final fate? The ultimate destiny of the cosmos hinges on a simple but profound question: will the universe expand forever, or will it one day collapse back upon itself in a fiery big crunch? The answer is written in the total density of all matter and energy, a cosmic ledger where dark matter is a crucial accountant. This critical density is known to cosmologists as omega. If omega is greater than 1, the universe has enough gravitational pull to eventually halt and reverse its own expansion, leading to that final collapse. If omega is less than 1, gravity loses its cosmic tug of war, and the universe will expand forever into an ever-cooling darkness. And if omega equals exactly 1, the universe is perfectly balanced or flat, expanding forever but at a rate that asymptotically approaches zero. For decades, astronomers like Dr. Wendy Friedman have led ambitious projects to measure the universe's expansion rate and its total mass energy content. Their painstaking work has revealed a cosmos that is, in fact, geometrically flat. But this seemingly simple answer holds a deep paradox. The combined gravity of all the ordinary matter and all the dark matter we have mapped accounts for only about a third of what is needed to reach that critical density of 1. Something else, a mysterious repulsive force we call dark energy, makes up the startling remainder. This is where dark matter's role becomes both foundational and subtle. While dark energy now dominates the cosmic dynamics, driving an accelerated expansion, it was not always this way. In the earlier, denser universe, the gravitational pull of dark matter was the dominant force. It built the cosmic structures, the galaxies and clusters that define the visible universe. Its immense gravity acted as a brake on the expansion, slowing it down for billions of years. The amount of dark matter present was essential in shaping the initial conditions that allowed dark energy to later take hold. Its gravitational influence determined the specific expansion history of the universe, setting the stage for the transition from a matter-dominated to a dark energy-dominated era. So the hidden engine of dark matter is not just an architect of galaxies, it is a fundamental determinant of cosmic destiny. Its silent, persistent gravity helped craft the specific universe in which dark energy could emerge as the victor. This sobering thought pushes us to explore the mysterious relationship between these two titans, the one that builds and the one that ultimately tears apart, forever shaping the final fate of all that exists. Two invisible titans are locked in a cosmic dance that dictates the fate of everything. One partner, dark matter, uses its gravitational pull to build and bind the universe, drawing matter together into the great cosmic web. The other, dark energy, is a repulsive force woven into the fabric of space itself, pushing the universe apart in an ever-accelerating expansion. For billions of years, the dance was dominated by dark matter. Its relentless gravity acted as the great cosmic architect, sculpting the first galaxies and pulling them into the vast filamentary structures we observe today. The universe was smaller and denser then, and the gravitational handshake of dark matter was strong enough to slow the expansion, gathering the raw materials for everything we see. But as the cosmos grew, it began to thin out. The distance between galaxies increased, and the gravitational influence of dark matter weakened with that growing expanse. This was the moment the balance of power shifted. Around 5 billion years ago, dark energy emerged from the background to take the lead. Its repulsive force, once negligible against the collective pull of all that matter, began to dominate the cosmic dynamics. Now the dance has changed. Dark energy is stretching the very spacetime that dark matter uses as its stage. It is not destroying the cosmic web, but it is pulling on its threads, influencing how it will evolve far into the future. The clusters and superclusters of galaxies built by dark matter are now being pushed apart from one another at an ever-increasing rate. This is the Grand Tango, a push and pull across nearly 14 billion years. The structures we see today, the great walls and immense voids, are a frozen snapshot of this ongoing struggle. They are the result of dark matter's initial construction and dark energy's subsequent stretching. This dynamic interplay is the final piece of the hidden engine, revealing that its influence is not a static force but an evolving relationship. The ultimate fate of the cosmos depends entirely on the outcome of this dance, a silent battle between two unknowns that challenges us to find a deeper, unified theory behind the veil of our visible reality. Sometimes the most compelling clues are the ones that never arrive. The persistent silence from deep underground detectors has pushed physicists to consider even more exotic possibilities, particles that are not just weakly interacting, but almost entirely absent from the conversation. What if dark matter is made of something even more ghostly than the elusive WIMP? A particle that shuns even the weak nuclear force. Enter the sterile neutrino. Think of the ordinary neutrino, that cosmic willow, the wisp which streams through the universe, passing through entire planets with near indifference. It interacts only via the weak force and gravity. A sterile neutrino would be its incredibly shy cousin, a particle that feels gravity but ignores every other fundamental force. Its only connection to our world would be through a delicate quantum mechanical dance, occasionally oscillating into a detectable, ordinary neutrino. This fleeting transformation could be its downfall. Some theories suggest that sterile neutrinos are not perfectly stable and could slowly decay, emitting a faint, specific signature of X-ray radiation. Astronomers have scoured galaxy clusters and the diffuse cosmic background, searching for this telltale X-ray line, a single, sharp spike of energy that would betray the presence of this phantom particle. A few tantalizing, unconfirmed hints have emerged over the years, sparking intense debate, but the definitive signal remains just out of reach. The sterile neutrino represents a profound shift in thinking, a candidate so detached from reality that its only mark on the cosmos might be a whisper of radiation from its slow death. But what if we are looking in the wrong category entirely? What if the hidden engine is not a particle, but a cosmic fossil from the universe's very first moments? This idea leads us to primordial black holes. Imagine the newborn universe, a seething, chaotic cauldron of energy. In certain regions, density fluctuations could have been so extreme that pockets of space simply collapsed directly into black holes. These would not be the stellar mass black holes formed from dying stars, but far smaller and more ancient entities, some with masses comparable to asteroids or even large mountains. A vast, unseen swarm of these primordial black holes, drifting like invisible icebergs through the galactic sea, could collectively account for the gravitational effects we attribute to dark matter. For a time, this was a beautifully simple solution. However, observations have placed severe constraints on this idea. If the galaxy were teeming with enough Earth-mass primordial black holes to explain dark matter, they would constantly act as gravitational lenses. As they passed in front of distant stars, they would magnify their light, causing a predictable pattern of brightening, a phenomenon known as microlensing. Extensive surveys, like those from the Ogle and Subaru telescopes, have monitored millions of stars for years. They have not seen nearly enough of these microlensing events to support a universe dominated by such objects. The allowed window for primordial black holes as the primary dark matter has narrowed dramatically, though they could still play a minor role. These alternative candidates, from the spectral sterile neutrino to the fossil black hole, reveal the incredible creativity driving the search. They prove that the solution to this cosmic mystery may not lie in a single, elegant particle, but in a form of physics so unconventional that we have yet to conceive of its full potential. A cosmic car crash on an unimaginable scale offers perhaps the clearest view of the ghost we are chasing. The Bullet Cluster is a system of two galaxy clusters that have violently collided, and the aftermath has created a perfect natural experiment. When these immense structures slammed together, their different components behaved in dramatically different ways, revealing their fundamental nature. The stars within the galaxies, vast as they are mostly empty space. During the collision, these stars passed right by one another like two swarms of bees, largely unaffected. The dominant form of ordinary matter in a cluster, however, is not the stars, but a superheated, thin gas that fills the space between them. This gas is detected by its intense X-ray emission. During the collision, this gas behaved like a fluid. The two clouds of gas smacked into each other, creating immense friction and pressure, slowing down dramatically and piling up in the center of the wreck. This is the sticky, interacting nature of normal matter. But the true revelation came from mapping the total mass of the system using the subtle distortions of gravitational lensing. These maps showed the true gravitational bulk of the clusters was not located with the piled-up gas in the middle. Instead, the mass had sailed clean through the collision site, residing in two distinct clouds that now flanked the central gas on either side. This was the dark matter. Because it does not interact with itself or normal matter except through gravity, it was completely unaffected by the cosmic traffic jam. It felt no friction, no pressure, and simply continued on its trajectory, separating itself from the visible material. For astronomers like Douglas Clow, who led the pivotal study, this was a eureka moment. It demonstrated that most of the mass in the universe is not only dark, but it is fundamentally different from the atoms we know. It is a ghostly substance that can pass through itself and through us. This observation poses a monumental challenge for theories of modified gravity. How could a change in the law of gravity cause the strongest gravitational effects to be physically separated from the location of the visible matter? The bullet cluster stands as a stark pillar of evidence, a cosmic snapshot that solidifies the case for a hidden engine made of unique, collisionless particles. It shows us that dark matter is not a mere abstraction, but a physical substance with a tangible presence, one that can be pulled apart from the ordinary world in the most dramatic fashion. We can rewind the cosmos from the comfort of a computer lab. Supercomputers act as digital time machines, running vast simulations that chart the evolution of the universe from its first whispers to the galactic empires we see today. These are n-body simulations, where the n stands for an almost unimaginable number of simulated dark matter particles, often in the billions. Scientists begin with the precise initial conditions imprinted in the cosmic microwave background that fossilized light from the infant universe. They program in the known laws of physics, primarily gravity, and then set the simulation in motion. What unfolds over months of computation is a breathtaking cosmic ballet. You watch as those subtle initial ripples amplify, as gravity pulls dark matter into an intricate, web-like structure of filaments and halos. This is the birth of the cosmic web in a box, a virtual creation that mirrors our own observed universe with stunning accuracy. Projects like Illustris TNG and Eagle have become legendary in this field. They do not just simulate dark matter, they also incorporate the complex physics of ordinary gas, star formation, and supermassive black holes. The resulting virtual universes are not perfect matches, but they are profoundly similar, producing realistic galaxies with the right shapes, sizes, and distributions. This success is a powerful validation of our standard model of cosmology, lambda CDM. But these simulations are more than just cosmic movies, they are crucial testing grounds. Researchers can run the tape again with different rules. What if dark matter particles were warmer and moved too fast to form small structures? The simulation shows a universe with far fewer dwarf galaxies than we see. What if dark matter could interact with itself, creating a kind of dark light or dark friction? The simulation reveals how that would smooth out the dense centers of galactic halos, potentially solving the core cusp problem. By comparing these alternate universes to our meticulous maps of the real sky, we can rule out some ideas and strengthen others. This computational principle is a fundamental part of the hidden engine, a theoretical proving ground that directs our telescopes toward the most promising corners of the mystery. It allows us to ask what if, and then see the answer unfold over billions of virtual years. Our own cosmic neighborhood holds a deep and puzzling silence. The grand simulations that so accurately predict the cosmic web also forecast a specific future for a galaxy like our Milky Way. They tell us it should be orbited by a vast swarm of thousands of smaller dark matter clumps, each a potential site for a tiny, faint dwarf galaxy. Yet when we scan the skies around us, we find only a few dozen of these small companions. The overwhelming majority are simply not there. This is the missing satellites problem, a quiet but persistent crack in the foundation of our understanding. Where did all those predicted galaxies go? The lambda CDM model is clear. Cold dark matter should clump efficiently at all scales, filling large halos with a rich population of smaller subhalos. The fact that we do not see them as luminous galaxies suggests something crucial is happening on these small scales, something that either prevents stars from ever igniting or makes these tiny galaxies incredibly difficult to detect. One compelling solution is that the vast majority of these subhalos are not missing at all. They are just dark. Picture a tiny, isolated clump of dark matter. a ghostly island adrift in the Milky Way's vast halo. Its gravitational pull may be too weak to effectively capture and hold onto the ordinary atomic gas needed to form stars. These subhalos would be pure dark matter, invisible cosmic fossils that exert a gravitational tug, but emit not a single photon of light. They are the hidden engine running in complete silence. Other processes could also be at work. In the early universe, the intense ultraviolet light from the first stars and galaxies began to reheat the cosmic gas, an event called reionization. This pervasive radiation could have heated the gas within the smallest halos, preventing it from cooling and collapsing, effectively starving them of the fuel for star birth. Furthermore, in those small halos that did manage to form a few stars, the first supernova explosions would have been cataclysmic. These stellar detonations could have blown the remaining gas clear out of the weak gravitational grip of the small halo, shutting down star formation for good. This delicate interplay between dark matter's gravitational architecture and the violent astrophysics of ordinary matter is key. The missing satellites are not a refutation of dark matter, but a clue that the hidden engine does not work in isolation. Its grand design is filtered through the complex, messy physics of light and gas, a partnership that we are only just beginning to decode. Perhaps dark matter is not entirely silent. The persistent small-scale puzzles, like the strangely smooth centers of dwarf galaxies, suggest its particles might occasionally speak to one another. This idea forms the core of self-interacting dark matter, a theory that adds a new layer of complexity to the hidden engine. In the standard model, cold dark matter particles are ghosts that pass through each other without a trace, governed solely by gravity. But what if they possess a subtle ability to interact through their own unknown force? This is the proposal of SIDM. It suggests that dark matter particles have a small but non-zero chance of colliding and scattering off one another, much like billiard balls when they come sufficiently close. This tiny interaction cross-section would be negligible on the vast scales of galaxy clusters, but it could have profound effects within the dense, crowded centers of galactic halos. Theorists like Dr. Manoj Kapling have shown how this simple change can resolve long-standing tensions. Within a dense dark matter halo, these occasional particle collisions act as a transfer of energy. Particles from the outer, slower-moving regions can scatter into the high-speed inner core, while faster inner particles can be kicked outward. Over time, this energy exchange acts like a form of dark matter friction, redistributing the particles and smoothing out the predicted sharp central cusp into a flatter, constant-density core. This elegant process can explain why many observed dwarf galaxies lack the dense central peak of dark matter that pure simulations predict. The hidden engine, in this view, is not just a collection of inert particles, but a dynamic fluid with its own rich internal physics. The key test for this idea lies in the shapes of dark matter halos and the aftermath of cosmic collisions. In a purely collisionless system, dark matter halos can become significantly flattened or elongated. But if dark matter particles are constantly scattering, they will tend to smooth themselves into more spherical and symmetric configurations, especially in their dense centers. Furthermore, during galaxy cluster mergers, the behavior of the dark matter could reveal its self-interacting nature. If the dark matter scatters even a little, it would lag behind the collisionless stars, creating a slight but measurable offset that next-generation telescopes hope to detect. This principle transforms our search. We are no longer just looking for a single, isolated particle, but for evidence of an entire dark sector, a hidden universe with its own forces and interactions. The engine powering dark matter's influence may be far more complex and dynamic than a simple gravitational anchor, suggesting a cosmic conversation happening just beyond our perception. A faint, high-energy glow could be the ghost's final signature, while direct detection experiments listen for the quiet bump of a dark matter particle. Another strategy scans the cosmos for the aftermath of its destruction. This approach, known as indirect detection, searches for the standard particles created when dark matter annihilates or decays. The principle relies on a fascinating possibility that dark matter could be its own antiparticle. If this is true, then when two dark matter particles collide, they would annihilate each other in a flash of energy, transforming into something we can see, such as gamma rays, neutrinos, or positrons. It is the hidden engine revealing itself not through a whisper, but through the echo of its own demise. The universe itself becomes our laboratory for this hunt. Scientists use powerful telescopes to scan regions where dark matter is predicted to be most densely concentrated. The center of our own Milky Way galaxy is a prime target, a place where the gravitational pull is so immense that dark matter should swarm in incredible numbers, increasing the chance of these annihilations. Another promising location is within dwarf spheroidal galaxies, small, faint satellites of the Milky Way. These galaxies are intriguing because they appear to be made almost entirely of dark matter, with very few stars to create competing signals. For over a decade, the Fermi Gamma Ray Space Telescope has been mapping the high-energy sky, meticulously searching for an unexplained excess of gamma rays emanating from these dark matter hotspots. The data is a complex puzzle, as astrophysical sources like pulsars also produce gamma rays, requiring scientists to carefully tease apart any anomalous signal that could point to dark matter. Meanwhile, other experiments look for different messengers. The Ice Cube Neutrino Observatory, a cubic kilometer of ice deep under the South Pole, is watching for neutrinos. The theory here is that dark matter particles could become gravitationally trapped in the core of the Sun. Over time, their density would increase, leading to more frequent annihilations that would produce a steady stream of high-energy neutrinos shooting out from the Sun's center. Ice cubes, thousands of optical sensors are waiting to catch the faint blue light from a neutrino interaction, a signal that could have a dark matter origin. This global effort to catch the indirect fallout of the hidden engine is a crucial complement to the silent waiting in underground labs. It searches for the engine's exhaust fumes in the depths of space, hoping to catch a glimpse of the physics that powers its silent, pervasive influence. Deep beneath the Gran Sasso mountain in Italy, a persistent rhythm has been detected for 20 years. The DAMA/LIBRA experiment, shielded from cosmic rays by a mile of solid rock, has reported a signal that rises and falls with the seasons. Its detectors, made of highly pure sodium iodide crystals, pick up a faint oscillation in events, a whisper that peaks every June and fades every December. The team behind this long-running project argues this is the signature of our entire solar system sailing through the galaxy. As we orbit the Sun, the Earth's velocity adds to or subtracts from the solar system's speed through a hypothetical river of dark matter particles that permeates the Milky Way. In June, when our planet's motion is aligned with the galactic flow, we should plow into more dark matter, creating a higher interaction rate in the detector. In December, when our motion is opposed, the relative speed drops and the signal should diminish. This annual modulation is exactly what DAMA claims to see, a cosmic metronome ticking with the calendar. The elegance of this explanation is compelling, a direct detection that seems to fit a beautiful theoretical prediction. Yet this potential breakthrough exists within a storm of controversy. No other major dark matter experiment has been able to reproduce this signal. The far more sensitive liquid xenon detectors, like Xeno NNT and Lux Zeppelin, which rule out vast territories of possible WIMP interactions, have seen no hint of this seasonal wave. This stark contradiction forces a difficult question. Is DAMA seeing the hidden engine of the universe, or is it hearing an elaborate echo from its own experimental setup? Skeptics point to potential seasonal systematics, subtle changes in the underground environment, or even the influence of cosmic muons or radioactive radon gas that could mimic a modulating signal. The collaboration has worked tirelessly to rule these out, but the burden of proof in science is immense, especially for a claim that would rewrite physics. This 2-decade-long standoff is not a failure of science, but a masterclass in its rigorous, self-correcting nature. Extraordinary claims require not just evidence, but verification from multiple, independent angles. The DAMA signal remains a tantalizing but unconfirmed ghost in the data, a reminder that the path to the hidden engine is a narrow one, where hope and skepticism must walk hand in hand until the final, undeniable truth emerges. We are not just waiting for the hidden engine to reveal itself, we are trying to build one. Deep beneath the border of France and Switzerland, the world's most powerful microscope probes the fabric of reality. The Large Hadron Collider does not look for dark matter out in space. It attempts to create it from pure energy. This monumental machine accelerates protons to within a whisper of light speed, steering them into head-on collisions that concentrate a fleeting fire of energy not seen since the first moments of the Big Bang. In that microscopic inferno, the laws of physics allow for the creation of matter, and physicists hunt for the possibility that dark matter particles could be forged in the wreckage. The strategy is brilliant, but the detection is indirect. If a pair of dark matter particles were created, they would be completely invisible to the detector. They would carry away energy and momentum without leaving a single trace, like a ghost silently exiting a room. So instead of seeing the particles themselves, researchers meticulously comb through the debris of each collision, adding up the energy and momentum of every visible particle that is produced. When they find a significant imbalance, a consistent missing momentum that cannot be accounted for, it points to something invisible having escaped, a compelling hint that dark matter was there. To strengthen the signal, they often look for specific event topologies, like a single high-energy jet of particles recoiling against nothing but empty space and missing energy, a signature known as monojet events. LHC researchers emphasize that these collider searches are a crucial third pillar in the hunt, complementary to the deep underground listens and the cosmic telescope scans. A detection here would not only confirm the particle's existence but begin to reveal its properties, its mass, and how it might connect to the particles we already know. It is the ultimate act of cosmic archaeology, not digging up fossils, but recreating the primordial conditions to force the secret into the open. This human-made recreation of the universe's birth may be our best chance to finally witness the hidden engine spark to life. This invisible ocean surrounding us forces a philosophical revolution. For centuries, our understanding of reality has been built upon a simple premise, that what we can see, touch, and measure constitutes the tangible world. Dark matter shatters this assumption, revealing that the vast majority of the cosmos exists in a realm forever beyond our direct senses. We are like beings who have only ever perceived the foam on the surface of a deep ocean, suddenly discovering the immense, dark waters beneath. This is not a minor adjustment, it is a fundamental overhaul of our cosmic self-awareness. The philosopher Karl Popper argued that science advances not by verifying truths, but by falsifying wrong ideas. Dark matter is a perfect embodiment of this principle. We have not proven its existence by touching it, but we have decisively falsified the notion that the universe is made only of what we can see. Its presence is a ghostly signature written in the motion of stars and the bending of light, a reality we must accept through inference and mathematical prediction alone. This expands the very definition of scientific observation. Is it any less real to detect a gravitational footprint than to see a color with our eyes? We are forced to admit that our senses provide a profoundly limited window onto the true nature of reality. The cosmos operates on a stage where most of the actors are invisible, and we are merely audience members deciphering the play from the subtle movements of the scenery. This journey to find the hidden engine is more than a technical puzzle. It is a humbling reminder of our place in the grand scheme, pushing the boundaries of what we can know and how we can know it. What other profound truths lie just beyond the edge of our perception, waiting for a new way of seeing to bring them into focus? The next generation of cosmic cartographers is already preparing for launch, armed with tools of unprecedented sensitivity. Their mission is to map the invisible, charting the dark matter web with a precision that was once pure science fiction. The Nancy Grace Roman Space Telescope and the European Space Agency's Euclid Observatory are at the forefront of this new campaign. These are not just telescopes, they are dark matter detectors on a galactic scale. Their primary weapon is weak gravitational lensing, but refined to an art form. By observing the subtle, coherent distortions in the shapes of billions of galaxies across immense stretches of the cosmos, they will construct a three-dimensional map of the dark matter distribution. This is like moving from a rough sketch to a high-resolution topographic chart of the hidden universe. We will see the cosmic web in stunning detail, tracing the finest filaments of dark matter and measuring how this scaffold has evolved over billions of years. Any discrepancy between this map and the predictions of our best models could reveal the true nature of the hidden particles, whether they are cold, warm, or something even more exotic. On the ground, the hunt is also entering a new era. The silent underground laboratories are scaling up. Next-generation, direct detection experiments are being designed with multi-ton targets of liquid xenon or argon, vastly increasing the probability of capturing that 1 in a trillion interaction. But the real revolution may come from an entirely new approach. Quantum sensors are emerging, devices that exploit the bizarre rules of quantum mechanics to detect the infinitesimally small magnetic fields or energy deposits a dark matter particle might leave behind. These sensors operate at temperatures near absolute zero, in a state of such exquisite sensitivity that they could hear the faintest tick of the cosmic clockwork. For the elusive action, dedicated experiments are growing in ambition and scale. Initiatives like the International Action Observatory are developing vast arrays of powerful magnets and ultra-sensitive quantum amplifiers, scanning through millions of potential frequency channels, listening for the moment an action decides to transform into a microwave photon. It is a painstaking, needle-in-a-haystack search, but the haystack is finally being sorted with tools that did not exist a decade ago. Perhaps the most profound shift is the move toward multi-messenger astronomy. The hidden engine may not reveal itself through a single channel. The future lies in correlating data from gravitational wave observatories with the views from optical, X-ray, and radio telescopes. Imagine detecting a gravitational wave signal from a merging black hole, and simultaneously seeing a peculiar flash of gamma rays from the same region of space. Such a coincidence could be the signature of a dense clump of dark matter being disturbed by the collision. This unified approach treats the cosmos as a single, interconnected system, where the hidden engine leaves its mark in multiple ways at once. The tools to finally identify this cosmic ghost are no longer just blueprints, they are being built. We are on the cusp of turning a century-old mystery into a new chapter of fundamental discovery, an era where the invisible will finally step into the light. The profound mystery of dark matter has ignited a public imagination far beyond the halls of academia. This invisible cosmic substance has become a cultural touchstone, inspiring stunning planetarium shows that project the cosmic web across domed ceilings and best-selling novels that weave its enigma into the fabric of their plots. Documentaries bring the faces and fervor of scientists like Vera, Rubin, and Priyamvada Natarajan into our homes, transforming abstract equations into a human quest for understanding. This widespread appeal taps into something fundamental, a shared sense of wonder about the hidden architecture of our reality. It asks a question that resonates with everyone, not just physicists. What is the universe truly made of? This connection is nurtured by science communicators who translate complex ideas into the language of everyday experience, using analogies of invisible oceans and cosmic scaffolds to make the intangible feel immediate. The effort extends beyond passive consumption. Citizen science projects like Galaxy Zoo have empowered hundreds of thousands of people to become active participants in the search. Volunteers sift through gorgeous images from telescopes, classifying galaxy shapes and identifying gravitational lenses, tasks where the human eye and brain still outperform even the most sophisticated algorithms. This collective effort does more than just process data. It builds a bridge, allowing anyone with curiosity to contribute to the very edge of human knowledge. That sustained public engagement is the lifeblood of fundamental research. The telescopes mapping dark matter, the deep underground laboratories, and the powerful particle colliders are all supported by a societal belief in the value of asking profound questions, even without a guaranteed immediate payoff. The enduring allure of this cosmic ghost story demonstrates that the search for the hidden engine is not a niche scientific pursuit, but a shared human endeavor. It connects the most abstract theoretical physics with our innate, timeless curiosity about the universe and our own small, yet deeply significant, place within its vast, invisible framework. That relentless search for a cosmic ghost has quietly built a better world right here on Earth. The intense technological demands of hunting dark matter have consistently forced us to invent the impossible, creating a cascade of innovations that touch our daily lives. The first and most fundamental challenge is creating absolute silence. To hear the faint whisper of a dark matter particle, scientists must eliminate all background noise. This requires materials of unparalleled purity, substances so clean and free of natural radioactivity they were thought not to exist. The quest for these ultra-pure materials has pushed materials science to its limits, leading to new techniques for refining metals and growing crystals. These advances now find use in the most sensitive quantum computers and in medical implants, where biocompatibility and purity are paramount. The very same low background copper and high purity germanium developed for dark matter detectors are now critical components in next-generation electronics and diagnostic equipment. This is the hidden engine, not of the cosmos, but of technological progress, driven by a question about the invisible fabric of reality. The detectors themselves are marvels of precision. To spot the minuscule flash of light or wisp of charge from a potential interaction, physicists had to create sensors of incredible sensitivity. These super-cold, exquisitely tuned devices can detect energy deposits smaller than anything previously measured. This technology is now being adapted for new forms of medical imaging, allowing doctors to see inside the human body with unprecedented clarity and at lower radiation doses, potentially leading to earlier disease detection. The same principles that protect a dark matter experiment from stray signals are being used to develop more sensitive scanners for ports and borders, capable of detecting shielded nuclear materials and making the world safer. Beyond the hardware, the hunt generates an ocean of data. Sorting through the countless events in a detector to find the one that might be real requires sophisticated algorithms and powerful computing. The data processing techniques pioneered by collaborations like LZ and Xenon have driven advances in big data analytics and machine learning. These tools are now applied everywhere, from forecasting global weather patterns to optimizing complex financial systems and managing smart energy grids. The very way we handle immense, complex information has been shaped by the need to find a single, ghostly signal in a storm of digital noise. This global scientific endeavor also serves as a powerful blueprint for international cooperation. Thousands of researchers from dozens of countries work together seamlessly, sharing data and resources in a unified pursuit of knowledge. This model of large-scale collaboration, built on open communication and shared purpose, demonstrates how humanity can tackle its most complex challenges, from climate change to pandemic response. The tangible rewards of this cosmic quest remind us that investing in fundamental curiosity does not just answer profound questions. It builds the technological and societal foundations for our future. Science often advances most profoundly through what it cannot find. The decades-long search for dark matter is not a story of failure, but a masterclass in the scientific method itself. A cycle of asking, testing, and refining our most fundamental questions about reality. We propose a hypothesis, perhaps a new particle like a WIMP. That idea makes a prediction, a signal we should see in a deep underground detector or a specific pattern in a telescope's data. Then we build the experiment, an endeavor that can take years and the work of thousands, to put that prediction to the ultimate test. When the result is a profound silence, as it has been for so many searches, it is not an end. It is a powerful piece of data that carves away a vast territory of what dark matter is not. Every null result forces a necessary creativity, a push toward more exotic ideas like actions or sterile neutrinos, or even a reconsideration of gravity's own laws. This rigorous process demands a deep humility, an acceptance that our current models, however elegant, might be incomplete or simply wrong. The true engine of discovery here is not just the triumphant moment of finding an answer, but the quieter, more persistent work of learning how to ask a better, sharper question in the face of the vast and whispering unknown. The final frontier in this cosmic mystery is not just finding the ghost, but inviting it home. For decades, the standard model of particle physics has stood as a triumphant cathedral of human understanding, a complete and precise description of the known particles and forces that build our visible world. Yet for all its glory, it holds a glaring, empty room with no place for dark matter. The ultimate ambition is to build a new wing, a unified theory that seamlessly connects the world we see to the invisible ocean we know is there. This requires more than just adding a new particle. It demands a fundamental expansion of reality's blueprint. Supersymmetry is one of the most elegant blueprints, proposing that every known particle, from electrons to quarks, has a hidden, heavier superpartner. In this perfectly balanced cosmos, the lightest of these superpartners would be stable, neutral, and pervasive, a natural WIMP candidate that falls gracefully out of the mathematics. It is a theory that does not merely insert dark matter, but predicts its existence as a necessary consequence of a deeper, more beautiful symmetry in nature. Another profound possibility is that our universe has more dimensions than the three of space and one of time we experience. In these theories of extra dimensions, the fabric of reality is a multidimensional brain, and while particles of light and matter are stuck to our brain, gravity and dark matter could be free to propagate through the full, hidden bulk of higher dimensional space. This would explain why we feel dark matter's gravitational pull so strongly, yet cannot see or touch it. It literally exists in a dimension just beyond our perception. Then there are the portal models, which propose the existence of entirely new, hidden forces. Just as the photon carries the electromagnetic force, a hypothetical dark photon could act as a messenger, a cosmic diplomat that mediates interactions between our world and a hidden dark sector. This portal would be a subtle bridge, allowing energy and information to occasionally leak between the two realms, potentially explaining rare particle decays or faint cosmic signals that have no other explanation. The search for this ultimate framework is the pinnacle of the quest for the hidden engine. It is not enough to know what dark matter is, we yearn to understand why it is, and how its silent existence completes the story of the cosmos. Achieving this unification would be one of the greatest intellectual triumphs in history, revealing that the universe is not built from two separate sets of rules, but from one magnificent, interconnected tapestry whose final threads have been hiding in the dark all along. We are the rare, visible exception in a cosmos of invisible rules. Every star in the night sky, every planet, every living thing is made from the same 5% of cosmic material, a luminous scum floating on the surface of a deep, dark sea. The world we perceive with our senses is not the true reality of the universe. It is the special case, the anomaly. This cosmic perspective is both humbling and strangely unifying. The same invisible architecture that guides the spin of distant galaxies also cradles our own Milky Way. Its dark currents flowing through this very room, through you and me as we speak. We are not separate from this hidden ocean, we are adrift within it, our lives and our world shaped by forces we are only beginning to name. This realization can feel like a lesson in insignificance, reducing our home to a speck in a phantom vastness. Yet it also tells a story of profound connection. The calcium in your bones, the iron in your blood, every atom of oxygen you breathe was forged in the heart of a long-dead star. A star that itself could only form because a dark matter halo provided the gravitational cradle for its birth. We are not just living in a universe with dark matter. We are products of its silent, persistent influence. Our quest to find its source is the latest chapter in humanity's oldest and most vital project, the drive to understand our true environment and our place within it. From realizing the Earth orbits the Sun, to discovering we live in a galaxy among billions, to now accepting that the cosmos is built from a substance we cannot see, each revolution expands our home while redefining our part in it. Uncovering the hidden engine is not merely a technical puzzle for physicists. It is a fundamental step in answering the most human of questions. Who are we? And what is this magnificent, mysterious reality we call home? Our journey through the hidden architecture of the cosmos brings us to a final, humbling truth. We have followed the gravitational whispers from the spinning edges of galaxies to the silent depths of underground labs, exploring the ghostly candidates from WIMP to actions that might power this immense, invisible influence. We have confronted the possibility that the engine itself could be a rewrite of gravity's oldest laws. This search is far more than a technical puzzle. It is a fundamental redefinition of reality, teaching us that the universe is built not from what we see, but from what we can infer through reason, mathematics, and a persistent collective curiosity. Each null result from a deep underground detector, every precise map of the cosmic web, and all the sophisticated simulations are not failures, but steps forward, carving away the impossible to refine our questions. The mystery of dark matter's hidden engine remains, but it is a vibrant, active mystery, one that connects the largest scales of the cosmos to the smallest particles of existence. The next chapter in this story could be written by a new observation, a sudden insight, or perhaps even by someone hearing this now, inspired to look at the night sky with fresh eyes. If this voyage into the unknown has sparked your own curiosity, there are countless more cosmic secrets waiting to be uncovered. We would love to hear which part of this profound mystery captures your imagination most. Share your thoughts on what you believe the hidden engine could be, and join us as we continue to explore the greatest story ever told.